All right, let's get into it. Today, we're going to crack a really cool puzzle that comes straight out of a university linear algebra exam. It's a fantastic test of how the core ideas of linear algebra let us figure out the properties of a matrix even when we can't actually see the matrix itself.
Okay, let's dive right in. This is our challenge. We've got this 5x5 matrix, called A, but we don't know what it looks like. All we have is this thing called its characteristic polynomial. So our job is to figure out which of these statements about A is the right one. It looks a little intimidating, I know, but trust me, everything we need is hiding right inside this one equation.
So first things first, we've got to understand our number one clue, that polynomial p of t. This isn't just some random equation, okay? Think of it like a treasure map that holds all the deepest secrets of our matrix A. So what is it and how do we actually read this thing?
Well, you can think of a matrice's eigenvalues as its unique DNA. They're these special numbers that reveal its true identity. Seriously, they can tell us everything from whether you can invert the matrix to how it literally stretches and flips vectors around. And the way we find these eigenvalues? We solve this polynomial.
So the trick here is to break this polynomial down to find its roots. First, you can see that every term has at least a t cubed in it, so let's just pull that out front. And what does that leave us with? A simple little quadratic, t squared minus 2t plus 1. And hey, you might recognize that. It's a perfect square, just t minus 1 squared. Now, it's super easy to see what the roots are.
And there it is, the DNA of our matrix, the two critical pieces of information we've been looking for. Our eigenvalues are 0 and 1. We also know their algebraic multiplicity, which is just a fancy way of saying how many times each root shows up. Since we had t cubed, the eigenvalue 0 has a multiplicity of 3, and since we had t minus 1 squared, the eigenvalue 1 has a multiplicity of 2. These numbers, 0 and 1, are the keys we're going to use to test every single statement.
Okay, now for the fun part, the investigation. We have our eigenvalues, 0 and 1, locked and loaded. We get to play detective and use them to check each statement one by one.
Let's start with claim number 1. A is invertible. Now, being invertible is a really big deal for a matrix. It means you can undo whatever it does. So how can our eigenvalues give us a straight-up yes or no?
Well, this is a perfect example of how powerful eigenvalues are. There's a hard and fast rule in linear algebra. A matrix is invertible if and only if 0 is not one of its eigenvalues. And what did we just find? We found that 0 is an eigenvalue of A. So, case closed. Matrix A is not invertible. Statement A is absolutely false. One down.
All right, on to the second claim. Now, for this one, we're not looking at just matrix A anymore. We're looking at a brand new matrix, formed by taking the identity matrix, I, and subtracting A from it. But the question is basically the same. Is this new matrix invertible? And you'll see the logic is surprisingly similar.
And, the logic is almost identical. There's another rule that says the matrix I minus A is invertible if and only if 1 is not an eigenvalue of A. Why? Well, think about it. If 1 is an eigenvalue, that means there's some direction where the matrix A doesn't change anything. So when you do I minus A, that direction gets completely flattened to 0. And since we know for a fact that 1 is one of our eigenvalues, this new matrix I minus A is also not invertible. So statement B is false too.
Okay, buckle up for this last one. It's a little trickier. It starts with a condition if A is diagonalizable, which is just a way of saying the matrix can be simplified into a really nice, clean diagonal form. And then it asks about its rank. A matrix's rank is basically a measure of its output. You can think of it as the number of dimensions the matrix projects information into. Let's break this one down step by step.
So we have this awesome tool called the rank nullity theorem. It just says that for any matrix, its rank plus something called its nullity always equals the number of columns, which is 5 for us. The nullity is just the size of the space that the matrix squashes down to 0. Now that condition, if A is diagonalizable, is the absolute key here. It gives us a massive shortcut. It tells us that the nullity of A minus I is exactly the algebraic multiplicity of the eigenvalue 1 for A. And we already know that number. It's 2. So now we just plug it in. Rank plus 2 equals 5. That means the rank has to be 3.
Okay, so wait a minute. The math checks out. If our matrix A is diagonalizable, then the rank of A minus I is totally 100% equal to 3. So the statement seems correct, right? But here's the catch, and it's a big one. The statement starts with that huge word, if. We just proved that the rank is 3 if A is diagonalizable, but we have no way of knowing that it actually is. It's like saying, if it rains tomorrow, I'll take an umbrella. The logic is sound, but you don't actually know if it's going to rain. Since we can't prove the condition is met, we can't definitively say the statement is true. It's not the right answer.
All right, so where does that leave us? Let's do a quick recap. We've shot down statement A is not invertible. We've knocked out statement B, I minus A is not invertible either, and we've just shown that statement C, while it looks plausible, isn't guaranteed to be true. So, what's left?
And just like that, by a process of elimination, we find our answer. The solution was the one option saying that none of the other options were correct. It's a classic move on exams. By systematically proving that the first three choices are wrong, we're forced to conclude that D has to be the one.
But this was never just about finding the right letter on a multiple choice test. This was about seeing the really deep, kind of beautiful connections inside linear algebra. This problem made us use one little polynomial to understand invertibility, diagonalizability, and rank all at once. So what are the big takeaways here?
These ideas are the real treasure we've dug up today. Understanding that connection between the eigenvalue 0 and whether a matrix is invertible is such a powerful shortcut. And seeing how the rank nullity theorem and diagonalizability play together is a crucial tool. If you can really get these ideas down, you can solve not just this problem, but tons of others just like it.
And that really just leaves us with one final thought. We've only just scratched the surface here. This one polynomial told us so much about our mystery matrix. But there's more. Its other parts can tell us about things like the matrix's trace and its determinant. It's just wild how much information is packed into one little equation, right? The real question is, what else is hiding in there?